Hi guys, welcome to this unit. We are we're expanding on the things that we learned from before when we talked about the sun, basically, when it comes to other stars to the other stars in general. And we also learned about the HR diagram. Remember, the HR diagram classifies the stars based on their temperature, their surface temperature, that is, and also on their luminosity or their luminance, okay, how bright they are, I mean, intrinsically. So this is the classifications that we saw. We saw actually that the main stars lie on a diagonal, which is the main sequence stars. And then you have some off-diagonal stars that are actually cool, but big, meaning that they are luminous, that they're brighter than what they would have been had they been on the main sequence star. And those are on the right-hand side. For the most part, they're either red or yellow. Okay, so you have the red giants and the yellow giants. And then on the other side of the main sequence stars, you have the white dwarfs. Well, in these units, we're going to basically go through the life cycle of a star, and we're going to divide them into two different groups. You have the small stars, that are of the size of the sun or less. And then you have larger stars that are a little bit larger than the sun and above, okay? So that determines, in a sense, also the lifespan of the stars. One of the things also we learned is that what is the relationship between the mass and also the luminance. It turns out that there is a power law that basically gives us how much the star will basically shine, how much energy it's going to output per unit time, versus its mass, and there is that m to the power 3.5. Okay, that is, in a sense, it gives us a sense also onto how much the star is going to shine, and that determines, in a sense, its lifespan too, because the lifespan also is inversely proportional to the mass and also the luminance. So we have a factor of a mass to the power 3.5 in the numerator. I mean, it's the mass divided by the more mass, of course, the longer it should live. But then you have something in the denominator, which is the luminance. So that's going to cancel that close to the mass. As a matter of fact, the more mass, the lifespan is actually shorter, according to that law, namely T is proportional, or it's equal to 10 to the power 10, basically, which is about 10 billion years. That is the lifespan of the sun, divided by the mass, divided by the luminance in general, and the luminance is, in this case, so you have an inverse of m to the power 2.5. In other words, the bigger the mass, the shorter the lifespan of the star. So again, when we divide them into two, that will tell us how long they will live. And actually, we're going to explore in these units the process through which they live. Again, they start from a protostar, namely, for the case of small stars, it's only few light years of intergalactic clouds, basically, material, which is mainly hydrogen and helium, plus all the remnants from whatever supernova that happened in before, and whatever also processes from other or planetary nebula also. So in a sense that this is basically the material, the starting point for a small star, few light years, then it's going to start to come closer and closer together due to the force of the gravity. So this contraction will result in reducing, if you wish, losses of the potential energy due to the force of the gravity, and that is being converted into kinetic energy. Well, that is going to heat up the place where the material is going to concentrate, namely the starting point, which is in this case going to be the star itself. So it's going to be through a protostar. So it's going to go through the stage of the protostar. Then at some point, it's going to, because again, we're converting potential energy into kinetic energy. So that protostar starts to spin faster and faster. And as it does, there is an ejection of materials on the poles. And at that point, we are entering the main sequence star. We are in what is known as a pre-main sequence star. Still, the temperature is not high enough for that to trigger nuclear reactions in its core. You need at least a temperature of about 5 million Kelvin. And that starts with high enough pressure, that is going to start the proton-proton chain that we discovered for the case of the sun. So at that point, we're fusing hydrogen into helium. Well, a small star, as I was saying, lives longer. So it's going to start its starting point, basically, which is called the Zens. At that point, it starts from its main sequence life. I mean, at that point, and then it's going to spend that time, which is in the billions of years. But for the case of the sun, it's about 10 billion years. Smaller stars will live longer. Again, it's inversely proportional to the mass. Slightly bigger stars, they will live slightly shorter, and so on and so forth. So for the case of the sun, it's in its middle age, basically, it's about 4.5 billion years, still have about 5.5 billion years to go before it basically runs out of hydrogen in its core. As long as it's fusing hydrogen in its core, it's still a main sequence star. So what happened when it runs out of hydrogen in that case? Well, the core starts to contract. Because of that contraction, at that point, and the temperature starts to cool down. There is no nuclear reactions at that point. Okay, so the star starts to swell at that point because of other processes. Because actually, the shell above the contracting core starts to heat up due to the fact that, again, we're losing potential energy toward kinetic energy. And that shell has hydrogen in it, so that hydrogen starts to fuse again. So again, expanding, which means that the surface temperature now is larger. Now overall temperature starts to drop on the surface, and the star moves from the main sequence star to become a red giant. So you're going to spend a lot of time in that state, and the core keeps on contracting until its temperature reaches high enough temperatures for helium to basically fuse. Because remember, the star started with helium to begin with. About 25% of its material was helium, in addition to the fact that it made helium during its process when it was in a main sequence star. So now it has enough helium, but when the temperature reaches high enough temperature, around 100 million Kelvin, at that point for nuclear fusion, for the helium takes over. So basically the helium and the helium and the helium, 3 helium atoms, they, not atoms, nuclei, I should say, they fuse together to form carbon. Okay, so at that point, there is a new, if you wish, lease on life for the star, and it's going to start fusing that very rapidly, and the surface increases, the temperature, surface temperature increases, and actually it moves a little bit to the yellow, and it becomes a yellow giant, but then it's going to run out of that quickly also, and move on to expand again, becomes a red giant again, and at that point, it's going to go through several Myra stages, which is basically the star is going to be a Myra at this time, a Myra star, meaning that it's going to shrink, increase its temperature, fuse hydrogen, and at that point, the shell and helium inside. Then, once it does, it turns out that it's going to run out, so it's going to cool down, expand, and then shrink and expand, and so on and so forth. So that's why it's periodic behavior. And Myras, in general, variable stars, their surface temperature and also their luminance change over periods that can elapse for several months. So it's one color, then it's a different color, one size, different size, and so on and so forth. Meanwhile, it's again confusing those elements, and it's running out very shortly because, again, it started small, and at that point, that is going to expand. Every time it's going to expand, it's going to expel more and more materials, and that forms a nebula. Okay, a cloud that is going to expand, and in the same time, it's going to start cooling. And as it turns out, of basically all of that materials that it is shedding at that point, it's going to move on the HR diagram, and at some point, the only thing that is going to be revealed is the inside of the ever shrinking core. when I said at that point, the balance, which is due to the thermal pressure inside due to high temperatures and also the force of gravity, that is for a normal star. But then for a white dwarf, what prevents it from further collapse is another pressure, if you wish, that kicks in. And that is with higher and higher compressions, the electrons start to get very close from one another. And there is a principle in quantum mechanics called the Pauli exclusion principle that prevents two electrons from occupying the same quantum state. So two electrons cannot be in the same point. That is basically what keeps further collapse of a white dwarf. And the white dwarf in this case, because there is no nuclear reactions in it, so it's really only the heat that it had from before starts to cool down and keep on until at some point it's going to run out of that heat and becomes a black dwarf. So this is for a small size star. For a large size star, the process is first of all expedited. In a sense, you have more materials to begin with, and that more materials will make the nuclear reactions a lot faster through the proton-proton chain, and then the temperature are higher, that there is the other process, the CNO process. Carbon, nitrogen, and oxygen cycle, where they go through it and basically fuse again 4 hydrogen atoms and converting them into helium. So basically the process now is a double jeopardy, if you wish. You have the proton-proton chain, and then you have the CNO cycle that takes over. I mean, that also is concurrent with the other one, and that is possible in large stars, not possible in the small stars. So the star goes through its materials a lot faster and runs out of fuel, if you wish, a lot faster. And it's fusing heavier and heavier elements because now, as it runs out of fuel, the balance shifts toward the force of gravity. The force of gravity forces all of the materials inward. But that increases the temperature, and as the temperature increases until it reaches the billions of Kelvin, at that point, each time that the temperature reaches a new plateau, a new kind of nuclear reactions occur, meaning to maintain that balance between the thermal pressure and also the gravity. So that balance needs to be reached at some point. So as we move on with higher and higher temperatures, and each time we reach a new plateau, new nuclear reactions happen, and we start forming heavier and heavier elements, up to basically iron, because at that point, the shell structure starts to be like a parent, that there's a lighter elements outside, hydrogen, then helium, all the way to silicon and iron inside. Once iron is formed, it will take about a day, and that will require a huge amount of temperature, about 3 billion Kelvin. Basically, there is no further way for the star to make more temperature to maintain that thermostat, basically equilibrium, that thermal equilibrium. Because iron isn't, fusing iron, if you wish, is not an exoenergic reaction. It does not give you energy. It takes energy actually from the star, which means it cools it even further, making the process even faster through which the star will collapse on itself at that point. So it takes about a day basically when it starts making iron, and when it does, the process expedited very fast, and the star comes on falling on itself at that point on the core. Okay. As the material hit on the core, it bounces off of it with this speeds that are incredible, almost the speed of light. So it hits in, out, and then that incoming material that is falling on the star and the outgoing material that is coming off of the bouncing, they collide. And that collision triggers actually a new process, which is actually the supernova explosion. That supernova, the way I'm describing it, is of a type 2 supernova. In this case, it's an explosion of the star. The temperatures become so high. Now there is room for making heavier elements. Remember, the temperature is so high. Now we have a readily available temperature at those pressures. So now the rest of the elements in the periodic table get created because Iron has an atomic number of 26. And if I create all of these elements on the periodic table from the first period and the second period and the third period, and I stop at iron. So how in the world we're going to make cobalt and nickel and copper and zinc and gallium and germanium and arsenic and all the way to these elements on the periodic table? Well, the next step, which is the supernova, is really that causes the rest of the materials to get formed. Okay, so that is basically the supernova stage. Where we are right now, there must have been a supernova, because in our bodies we have all of the heavier elements past iron, including iron itself. So that is basically how the rest of the stuff in the periodic table is formed. Now, depending on how much mass you start with, if you have you started with bigger than the mass of the sun, but if you started with just enough the mass of the sun, just above it, then in this case, the collapse of the core will result in, again, those electrons to interact with the protons, basically fuse with the protons, forming neutrons. So there is an abundance of neutrons over protons at that point, just because of those electrons. They get smashed into the nucleus, and some of them fuse with the proton, basically through nuclear reactions, and form neutrons. So now the star is mainly neutrons. That's why it's called the neutron star. Okay, again, what prevents it from further collapse in this case is just, again, that same degeneracy, because protons behave like electrons also. They cannot go into one another because of the same principle, which is in this case called the degeneracy. Okay, so in this case, they stay in touch with one another and they get very close from one another. Okay, so this is a neutron star. But if the mass is even larger, that pressure from this degeneracy is overcome by the force of gravity. So in a sense, now we're going inside and creating a new thing, which we don't have physics for it to describe, which will go inside of it, and that becomes a black hole. Okay, so you have two possibilities. Black hole in size, depending on how much it is, should be smaller in size than a neutron star. Neutron star is about the size of a city, and a white dwarf is actually about the size of a planet like Earth. Okay, so this is basically, so white dwarf is the end of a small size stars. Neutron star and black hole are the end of a larger stars. So again, the process is similar in the beginning. For a large star, it starts as a protostar, then a pre-main sequence star, then a sequence star, main sequence star, and at that point, it's really going very fast, only within millions of years. After that, it's going through the stages again of a red giant, and then it's going to go process quickly, and then at that point, the collapse will result in a supernova of type 2. There is another type of supernova called supernova type 1, when you have actually a white dwarf and a regular star, part of a binary, and then the white dwarf, because it's supermassive and it's orbiting one another, and they get close, starts to feed off of the main sequence star, which is its neighbor at that point. And then as it feeds, it grows in mass until at some point it reaches a critical Chandrasekhar, basically a limit, which is about 1.4 the mass of the sun. At that point, it's going to go to supernova 2. Collapse, cause all kinds of things. So that is type 1 supernova. This is actually useful for other purposes. We'll discuss them down the road about the expansion of the universe. So this is, in a sense, the stuff that is related to that. Now, also the units talk about the neutron stars and also black holes. For the neutron stars, they're characterized again with the spinning. That's one of the things that we learned, how we discovered them, with periodic rotation that is within few seconds or fraction of seconds as they spin. So imagine a White House as it turns for the boats to come in. So that shine of light that is coming from the neutron star, depending on the angle, the orientation, obviously if it's oriented at 90 degrees, we're not going to see that light, but that's only a small correction. But if at any other direction, we're going to get that periodic motion. Again, that is the radio waves that was discovered, and then at the end it was explained because these things have super strong magnetic fields. There is a version of them called magnetars that are even have tremendous amount of magnetic field spinning at super fast, resulting in extreme high energy being emitted at those frequencies with this periodic motion. Again, you have the pulsars. Those are basically what we thought initially are, and then it turns out because they are pulsating, so those are pulsating stars. So that's our neutron stars. Now, black holes are characterized by the short side radius, basically at that point, and that is the event horizon. And I'm recording this one on the 13th of May. Yesterday was a big announcement from NASA. I don't know if you have had a chance to look at it or not, but they took a picture in 2017, but they just finalized basically the data analysis of our own black hole. This Milky Way has a black hole, which is about 4 million times the mass of the sun. And this is as opposed to the picture that was released actually in 2018 related to, again, observations that were made in 2017 for the black hole in M87, which is another galaxy about 50 million years away from us in here. And that is the first black hole that was taken picture of. But that black hole is supermassive. It's about 1,000 times larger than our black hole. So again, there are two types of black holes that we know of. There are the supermassive black holes. Those are basically, we don't know how they form, honestly. And then there are the stellar size, basically, black holes. There are few only masses of the sun. So those are the collapse through a supernova process, namely a supernova of type 1 or type 2, where basically they form those black holes. If you guys have any questions, again, there will be assignments. Please look at them. Please do not hesitate to contact me either via Canvas, or if you want to, we can meet on campus Monday and Wednesday. Thank you.